this class, we will do something we've done before, which is do inverse kinematics, but I'm going to use the nonlinear optimization solver we talked about, NLOP, to do the same thing. In this case, we'll do a two-link manipulator drawing the infinity figure, which is also known as the lemniscate. So again, as usual, go to tiny.cc MuJoCo, download the template called template_manipulator, unzip it in my project, then rename that, let's say manipulator_ik, make those three changes in main.c, make file, and run Unix. I don't have a run win for this because I've not really figured out how to use NLOP with Windows. And then navigate to the shell, that is to the folder manipulator_ik, and then do run Unix. And if you see a two-linked manipulator in front of you, that means everything you did is correct. So I'm going to do that right now. Okay, so that's the template manipulator. Unzip. Let's call it manipulator_ik. In here, we'll change main.c. Okay, so main.c, we will change this to this folder name to manipulator_ik. Change one, then we will go to make file and then change this to the root to manipulator_ik. We don't need to keep that open, and then run Unix. We'll change this to manipulator. Okay, so that's done. Now let's go to the terminal, navigate to this folder, cd documents, MuJoCo, my project, cd manipulator_ik, run. Okay, so the manipulator is in the default configuration, which is it is horizontal. Okay, so that works. Now let's go to the next part. Okay, so what I'm going to do here is, instead of doing this randomly, I just thought I'll just put my thought process on how I'm writing this code to do the IK as an algorithm, and I'll just follow these steps which I've put down here. So we'll follow these steps, and they are pretty much what I've discussed earlier in the initial value problem. You first create a function which gives you the necessary output given the input, and then a bunch of other things, right? So I'll just go through this, and hopefully that will be much clearer than if you want to modify, program another problem involving inverse kinematics, you can pretty much follow this recipe. Okay, so first thing is, I don't think I wrote down the optimization problem, but the optimization problem in this case is simply, given the joint angles, let's say Q1 and Q2 for the two links, I need to be able to produce the position of the end effector. Okay, so what I've done in this case is I've created a site, and the site is the tip position, and that basically gives me the position of the tip. So this is a change I've done in my manipulator, the double pendulum class. So let me open this. Look, next, I'm going to open the manipulator to show you what exactly is in there. Okay, so this is the manipulator.xml. I've basically put a site called tip, which is a circle at the end, and I have essentially asked MuJoCo to give me the position of that and also the velocity, though velocity is not needed in this particular example. And then I put a position velocity servo on each of those links. So as long as I put the control to be whatever position I want. For the first link, it'll go to that position using this PV servo. Okay, so we have that. And remember that if I want to get the position of the tip, I need to essentially get sensor data 0, sensor data 1, and sensor data 2 corresponding to the XYZ position. So let me just try to get that first before I go to step 1 here, which is creating a function which gives me the output, that the tip position given the input, which is the joint angles. So we will just sort of play with the file and then get to the point where we are doing step number 1. Okay, so what I'm going to do is I'm going to sort of create this code in my init controller, which is called at the beginning. And then once I get it working, then I'll move it to a different place. Okay, so as I said, you need to do tq pose t sensor data 0 and d 1 to get the 2 to get the x and z position of the tip. So p printf tip %f line yes, so it printed 0 0, which doesn't look right because the position of the tip is not at 0 0. It's the starting point of the green link, which is the 0 0. So what has happened here is this has not really propagated into the dynamics because MJ step has not been called. So you can call MJ step, or I recommend just using MJ forward with M and D as arguments. And now once you do this, it actually propagates into the system and it will give you the position of the tip, which is not clearly 0, 0. Okay, so now it stops. So now you can see it's 2, 1.25. The x coordinate is 2, the z coordinate is 1.25, and that's what I expected. Okay, so that's just showing how to access the tip position. Now let's sort of try to work towards the point where we are generating this function, which given the inputs for the angles produces the tip position. So let's define double xin2 equals, I can specify whatever I want for the position of the joint angle. So I'm just going to use what I've used previously, minus 0.51, because you see that this corresponds to the tip being at the on the horizontal. This is close to along in the same line as the joint of link 1, which is the green link. Okay, so let's double x in, double x out. This is going to give me sensor data that I need to initialize to 0. This is the tip position, and this one is I need to create a function with inputs x in, x out, and this x out should produce this data. So what I'm going to do is write this function right up here, void simulator x double x in, 2 arguments, in and out. Okay, so all I need to do is pretty much move this there. Okay. So x in needs to, well, here in this case, I need to specify x in. So dq pose 0 equals x in 0, and dq pose 1, which is the position, the angle for the second joint, equals x in 1. Okay, and then once it is set, that is the data is updated, I need to propagate that in the model so that it be MJ forward. And what comes out is the configuration of the manipulator in approximately this position. So then I need to read the position of the tip, which I'll do now by saying x out 0 equals t sensor data, and x out 1 equals that. And then if you, well, it might be best for me to print this in here. So I'm going to print X out now, just to show you that it actually does what I wanted it to. Okay, so it's set, the sensor data is set to X out 0 and 1, and then I'm going to read it out here. And if it is all right, then so this should be 1. You should actually see the same 2 and 1.25. Just that now I created a function called simulator. Okay, that doesn't look right. Let me. So it says 1.75 and 1.25. Okay, and then you saw that the magnet also moved. Okay, so what's going on there is, remember I have a PV servo, and that PV servo is setting the position to be by default 0, 0. So it's trying to set the manipulator to go to the horizontal position. So clearly that is what's probably happening, and then that's why it's moving back to this not to the position I wanted, but it's going back to 0, 0. So what I'll do here is I also specify DRL 0 equals Q pose 0, and so now I need to go by this. So the first one is the position command, so it'll be 0, and then there'll be if you specify CTRL1, that will be a velocity set point, which I don't want. I only want a position set point for link. That will be the number 0, 1, 2, so it'll be 2. 2 equals D equals. So if everything looks right now, I think it'll work. Okay, okay, so it not only it produced 1.75, and that's what I expected, and did not move. Right? So, okay, so the thing to note is that if you remove this, then it will also give the same result, 1.75, 1.25, which is the position in this particular configuration. However, it kind of settles back to this horizontal position because I've not specified DCTL, the control, the set point has not been changed. So if you want to set the set point as well as get the data, then you want to do both these things. Okay, so that's my simulator function. It gives me the X out given an X. Okay, now the next step is for us to go and open up constraint.c and sort of start including that inside the main.c. And the way I'll do it is I will first just include constraint.c. And remember that constraint.c, which we looked last time, has this main function, and you cannot have two main functions in your whole project. So I need to rename that. I'll rename that to inverse_kinematics. Okay. And so we'll just run it and see if we are able to incorporate that. Just doing it one step at a time, just so that we can debug any issues. So I've already put constraint.c inside this folder, so you don't have to do much, just include it. So go here on top, include constraint.c, and the change I need to make is open constraint.c. Okay. And I just don't want this. This is from the previous problem. Just delete that. Okay, so there's a main, and I can't have two mains. So I'm just going to write inverse kinematics. Okay, let me call this function within init controller just to check if my integration has all worked right. Go here in init controller. And I believe I don't want this for now. Let's just comment this. So now let's run this. Okay, so this is basically producing the output of that constraint.c, which is what we've talked last class. It will give this because it's a different problem, not related to this problem, but this just ensures that we're able to integrate these two codes together. Okay, the next step is we need to move the simulator from where we have it right now in main.c to constraint.c. And the reason I want to do that is because our optimization will happen in constraint.c. So I want it to be in that place. Actually, there's no issues having it here. You need to define it in the beginning of constraint.c if you still want to keep it in main.c. But I just think it's much easier to move it there because it's easy to work with it. Now, here's something which I think is sort of new. We've not done this before. When we will call x in, x out, we will have to get access to d, right? So we need to make an external variable. In fact, let me just first put it and show you that it doesn't work. And that's where I need to define d as an external variable. So let's just first just copy this and let me show you how it breaks, and then we'll fix it. So let's take this, comment it out, do constraint.c. Let me go above here. And then I want to maybe check this. So what I'll do is I'll check this by calling it in the inverse kinematics module, right? So I go down. And then, you know what, let me just find it here. I just need to copy these things down, just exactly how they were. So take these things, this code, and right now I'm moving it there because I want to test if this is able to produce the same result as I got with init controller. X in, X out, okay. So it should produce the same result, which was 1.75, 1.25. Okay, run this. Okay, you see there's an error. It doesn't know what, well, all the errors are related to this variable d, which is in constraint.c. And as I said, it has no clue what this d variable is because it's not been defined. So what I need to do is, and I've done this in the previous class, which is I can define extern mj data. Let's see if I got the syntax right. So mj data. Yeah, so I can do it this way. Extern. Okay, and let me just put it down here. Okay, and I think this will work just fine. Oh, I need to also define m. My bad. Extern mj data. Run this, it should just work fine. So it just produced the same result, 1.71. So everything works. Now, however, there's a twist here. I'm not going to try to use d. I'm going to use another data variable called dsim. And this is where I think is kind of interesting, which is when you're doing these simulations, let's say of let's say a quadruped, and you need to simulate the system ahead in time. But as you simulate, you need to find torques or control variables, and those control variables need to be assigned based on a model of the system. So you need a model of the system in order to find the torques, but you are already using the model to do a forward simulation. In other words, you need two models there. You need one model to do the forward simulation, and you need one model at every time step to do some computations to find the torque. In order to do that with MuJoCo, what strategy you can use is this. You can keep track of two data variables, d, and I'll call that dsim, where d is the robot, that is a manifestation of the actual robot. It's going to be something which you simulate ahead for whatever seconds or time you want to. And then dsim is your data structure, which will keep track of any calculations you want to do at every time step. So you can reset it any way you want. You can set it to any angles you want, and it will not be linked to d. I'm going to create this new variable, and then as I use it, you'll see the advantages of doing this kind of thing. So let me create a new data variable. I will go here, just copy this. Let's call that dsim. There are three places where you need to, or two places, three, including this one, where you need to make these changes. Once you define dsim, which is my data structure, I need to go to the main block, right, where this is done. So here you are trying to get data which is associated with the model M. Okay, so it's initializing D, the data structure. And then there's another place right down where you destroy it at the end of simulation. right here. So you can just try it. Okay. So once you've done that, I can go to constraint.c now and then change this to dsim. So remember that D is the actual robot. It's like the manifestation of the robot, but dsim is a data structure which I'll be using for calculations. So I want to give dsim access to my constraint.c because constraint.c would be called every time in my controller to compute torques or control or whatever you want. So there should be no reference of D here because that's the actual robot. If this was put on the actual robot, then you don't have access to D, you only have access to dsim. So dsim. Okay, note the call here now is done with mdsim and not md. Okay, all that's done. And if everything works fine, no errors, it will print the same thing. Okay, it's printed the same thing. Our integration of constraint.c and creating the new data structure worked. Okay, so done with 3. Okay, next, now what we'll try to do is we will try to do this exercise of writing the constraint.c file such that we are able to position the tip at the position we care about. So right now it is at 1.75, 1.25. Let's try to set it initially to a different position. Let's say 1.75, and so that's on the x-axis and maybe 1 on the z-axis or 1.5 on the z-axis. And that is just checking programming the constraint.c to do one pose. So once I figure out one pose, I can just do it for a series of poses to get the lemniscate. So let's program inverse kinematics to do the optimization for a single pose. So what I'll do is first, in order to integrate this code with my main.c, I'm just going to call this. I believe I called that already. Yeah, I called it already. But what I want to do is I want to send in my x in from here rather than set it up here, because then what's going to happen is every instant I will tell it what the current x in is. It'll compute the new x in, which is angles, and then it'll give me the output. So I am going to define it here. I am also going to define a new variable called xref, and this is where I want the tip to be. And as I said, let's put it at 1.75 and 1.5. So that will be a reference. So I need to send these two variables in inverse kinematics. Okay. So let's go to inverse kinematics. X2, xref2. Now this will go away. This will go away. This will go away, and so on. Okay, now I have access to xin and xref. And what I want to do here is now start thinking about the optimization problem. So my optimization problem, maybe I should write it here since I did not put it in my slideshow. Optimization problem. Okay. Here the cost. The cost is, there's nothing to really optimize it, it's put 0. The constraints are, there are two constraints, equality constraints. If there is a x target and a z target, then that x target should be sensor data 2, that's from z, and sensor data 0. So that would be c equality 1 and c equality 2. And what are the decision variables? There would be x in, which would be q1, q2, These are my joint angles. And then our bounds. So I need to set some bound. I'm just going to put bounds for Q1 and Q2 are in between minus, let's put 3.14 pi to 3 plus 3.14. Okay. So with this in mind, we can just think of formulating the problem within an LOP. Okay, cost is zero equality. So there are two decision variables, and then these are the bounds. Let's go right to here. And decision variables are 2, equality are 2, no inequalities. The bounds are minus 3.14, minus 3.14, and the upper bound is 3.14, 3.14. Okay, that's done. We created the optimization problem. We set in the lower and upper bounds. We don't have any parameters in the cost, so let's just eliminate this. When no parameter there, you want to put null here. There are two equality constraints. Let's just put that to, I don't know, -8 is fine, I guess. We have no parameters, set that, commented out. Here we want to put null because no parameters are passed. My inequality constraints are not there, so get rid of that. Okay, now we reach the point where this is the termination criteria, which is 1e -4. When change in x is less than 1 -4, we'll stop. And then we want to give an initial guess. But the initial guess is already coming from here. This is our initial guess, which is provided by init controller. So let's just, you don't even need this, it's already there. However, when we optimize now, this should be x in. Okay, so once the optimum solution is produced, it will have two x's. So I have two x's, and then this will be the output for the cost. So I have just that. So this will be x in. So once you send in an x in, which is your current state, it will try to do the optimization and produce new xins, which satisfies the constraints, and that will be here, and that will be just be printed on the screen. Okay, so now let's go and start programming the other things. So first of all, we have no parameters. Comment everything out. We have the cost is 0, so don't need all this. We don't need this, so it's just 0. Okay, now we do have equality constraints, but we don't have any of these bounds. So I'm going, the parameters. So just comment it out. So our results should be saved in these two variables. Result 0 equals result 1 equals. Okay, so what we need here is something like this. Okay, so I'm going to try to program this. Okay, so clearly, if you want to get X target and Z target, they come from the reference, right? The reference is something which I send, which is this. It's sent to inverse kinematics. It is right here. So if you want to send reference to my equality constraints, you actually have the options to pass it as a parameter using equality data. Okay, so that's something which you can do using this structure, which I'm going to skip that, but you can do it. Instead of defining it this way, that is passing it as an argument, I'm just going to make global variables called X target and Z target, and then assign them right here. So here, when this comes in through inverse kinematics, I'm going to set X target to be xref 0 and Z target to be xref 1. And I need to define these variables as global variables. Let me do this, just that on top. X target, okay. And now that we've got that, we have already computed, well, we know X target and Z target. So I'll just put it here. Okay, what is missing is these variables. We have this in MuJoCo, but they don't really mean anything because we have not set the state. So I need to set the state. And this is where I have to use the simulator. So I need to call simulator. My inputs to simulator as xin. So xin in this case is going to be the optimization variable, which has been circulating in my equality. So it'll be x. And then x out is my output, which I need to, by the way, define. So double x out 2 equals 0. And remember that x, this is itself actually is x out, right? Because I set the x out to be dsense data. So I really need to assign them to x out 0, x out 1. Yeah, I think I'm all set. I've pretty much done programming the nonlinear root finder. Okay, so there are errors. There's a lot of errors. This is on line 94, 98. Let's go down. 94 is, oh yeah, this is my bad. It should be commented out. We are not using inequalities. Let me just try it again and see if it produces the errors. Yeah, it worked. Okay, so now this is, well, we'd asked it to be at 1.75. There's quite a few things going on. First of all, the manipulator was straight, and it also says that this is the optimal, but there's no way to check this. How do I check? So it says that this is the optimal value, but I have not really set that value in the manipulators to us to actually see it. So what I forgot to do is, once this produces this x in, I need to set it up. So this is some code which I wrote down right here. So what I need to do is, I need to set whatever x in comes to qpose, and then I need to set the control. And if that works right now, it should actually sit at 1.75. Okay, so it's saying minus 0.34. It looks good. Let me just try to get the sensor data. So that is also here. Okay, so if everything works right now, I should see in what prints here should be 1.75 and 1.5. Okay, so it did not, because I clearly should do MJ forward here. That MJ forward, which is in simulator, is for dsim, so for D. Okay, so it looks good. I have the tip exactly where I want it. So the optimization stuff actually works. I think there's one problem though, which I see in this code, but let's try to see if we can discover it in writing the code. Let me just move on, since we've already achieved step number 2. Now create a function for xref. Okay, so this is now, so xref right now, I just put some random value 1.75.75. But what I want to do now is I want to create a function which basically gives me the position on this lemniscate as a function of time. So the moment I give it time, it will tell me that the first position is here, second here, third here, and so on. And so that way I can just keep calling this and then making it plot this. What I'm going to do is I'm going to search the formula for lemniscate. And I think Wolfram is a good place. Okay, so this is the lemniscate and a lot of equations for it, but the equation I'm mostly interested in is the parametric equation. So here A, I think is, it actually might be either this or the whole length of it. A cosine t, so t is the parameter. So if as t goes from 0 to 2 pi, it basically draws the whole lemniscate. And so these are the formula that I'm interested in. So I'm going to make a function called curve, I guess. And so that function will produce the xref 0, xref 1 based on parameter A, which is the size of the lemniscate, and T, which is going to be, in this case, the time. So let's create this function first, and we'll go from there. Okay, so main.c, I'm going to call it main.c because this is where I'll provide that to the constraint optimization solver. So let's say call it here. So let me call it curve. Its input could be time. So given the time, it will produce x and xref. I want to make a as a global variable. I also want to actually, instead of treating that as t, I want to make it omega times t. That way, by controlling omega, I can control the speed. So I'm going to have two variables here. So this should be double t, and then output would be double xref. So let's see. So I'm going to just copy this formula first. So xref 0 equals a times cosine omega times t. Then there's a denominator term. Let me just make a function called double, which will be 1 plus sine omega times t into sine omega times t. And then that should be then x ref 1 equals a times sine of omega times t into cosine omega times t divided by denominator. I think this looks good. The only piece missing is there's a which I've not defined, and there's omega. So it'll give me some errors. So just put double a equals, and let's just 0.5. So remember the length of the manipulator is about I think 1 meter is the length of each link, and if maybe 0.5 is to be 0.25, and then let's just set omega to be 1. Okay. And then we can change that speed. So let's just make this global variables, put them on top. Okay. Now let's just go back here. So this is basically the equation in lemniscate. If I don't have the center line, then it's actually we'll try to draw the lemniscate right here, which is going to be really difficult for it to do. So I need to move that lemniscate from here at the tip of joint 0 or joint 1 to somewhere here. So I'll have a variable called center x and center y so that I can just move it. So let me add to this double center x, center y, and I'll define that in just a bit. But let me go back and move the curve or translate it by the distance equal to center x. Center y. Okay, and then let me just check this for, well, it will not work, right? So let me just put some value for center x and center y. Let's say 1, and center y is, so the center z, sorry, I should put y. That should be 0. So which is saying that I'm going to put it approximately, let's say about here. So let's go back and just change center y to center z. Okay. And let's check this function works or not. So at time t equals 0, I would say call curve with time t equals 0 xref, and then I want to basically use, I don't want to call this, but I want to call curve. So let's call it this way, but I need to define xref. Okay, let's try this out. Okay, that doesn't look right. So that's x in, that's xref. Maybe I should just print what xref looks like. Zero, zero. Okay, that doesn't look right because if t is 0, then this thing is 1, denominator is 1, and then this term is going to be 0 because there's a sign. So it's xref 1 should be center z, which should be 0. Oh, I see the problem. Okay. Okay, so the problem is this, which is, and I completely forgot, this position is not 0, 0, it's actually it's 0, 1.25. So it's above by 1.25. So I need to move that. Let me just make it 1.25. Okay, so now it is, now I'm saying it should be here. 1.25 is the height of it. So let's try this and see what we get. Yeah, it's much better. So 1.25, 1.25. You got 1.25, 1.25 because of this formula, the curve. If you look here, if you put t equals 0, we have denominator is 1. As I said, center x is 1.1 and a is 0.25. And so 1 plus 0.25, 1.25, and then z was set to 1.25. So it all looks good. It just is doing what we wanted to. So function works. So we've created the function. Now program init. So we did this also. We program init controller to set the curve, center, initial, center. Okay, but actually we've not quite done this. So what I'm going to do is, and this is just to make my life easy later on, which is instead of me specifying, sort of automating the process of making this start point to be here, what I'm going to do is, I know that the position of, when I put minus 0.51, I know the position is somewhere here. I'm just going to use it somewhere here. I'm just going to use this position to figure out where I need to put the center. So in other words, I will pre-specify this position. This is where I put these angles and I propagate it through the system. It predictably puts the manipulator here. I will use that sensor position to put the center at a distance of a to the left. That's all I'm trying to do. So let's do that. And that's just one of many ways of setting up the initial condition. Okay, and I'm just doing it because just to be consistent with what I did last time when I did this for a circle. Okay, so here's how to do it. This. So this is what I'll do. I'll first get x in. I will then send it through the simulator. And it will give me x out. Define double x out equals 0. Okay. So now once I propagate it through x in, it will give me the output of the end effector position, which will be an x out. Let me just print that. Okay. Let me not do any of these other things. Solve this. Okay, so what it's saying is that if you put minus 0.5 and 1, you get that position, which is okay. Now, remember that that position is here. Okay, so that corresponds to x0 plus a and y0. In other words, x out 0 equals center x plus a, and x out 1 equals center y plus 0. So that's that location. Okay, so I'm going to use this fact to now compute what the center should be, because I want to start over here, and so that center is a free variable. The center x equals x out 0 minus a, just moving things to the left side. Center y equals x out 1. That's it. Okay, the center is set. The a is set by me, so it's going to override the center. And now we can say curve 0 comma x ref, and then we can pass it through inverse kinematics, mj forward, and printf. Center z. Yeah, this not surprising and give me the same one. I just took it, fed it back to the, I took this xref and fed it back to the inverse kinematics, and it obviously gave me the same result. Okay, so this is just getting me, I programmed the init controller to give me the initial position I wanted to be at, and I was able to program inverse kinematics. Now, the only thing left now for me to do is to make this, create this manipulator to just go hop around this. Just keep going. How can I do that? Well, each time I need to define a different reference. And once I specify the reference, I need to go to inverse kinematics, which will compute the joint angles, put that in the system, and then do the animation. So the procedure is use the time to find the reference position, feed that reference position into the inverse kinematics. It'll give me the joint angles. And remember that the inverse kinematics module use dsim to compute those angles. Those angles come back to the main block, to the D, and once I propagate to the system, it'll actually start moving and keep doing that. So let me do that. So this part is initialization of the controller. Now I'm just have to call the same thing over here. So it's pretty much, this is a copy paste. Take the important parts and copy paste them here. So first of all, let's take this. First, I need to define xref. Okay, so this will happen every single instant of time. Next, I take curve 0 time. But here, remember, it's not just the time 0, but it's going to be every time goes into that curve, gives me xref. Then I go to inverse kinematics. So that will be x in. That x in will come, and I actually do not need to set the pose. I just need to set the controller. So this is just setting the initial pose. Set initial pose, and then set initial control. But once I do it once, I don't need to cut the initial pose because that will automatically set by this. So I need to change this to be x in 0 and x in 1. Okay. And once it's done, I believe what will happen is it will keep moving. Now, x in has not been defined, so I need to define x in. And I have an option to define the way I want, but what I'll do is I'll take the position, the previous time step in order to initialize it. So that will make it easy for the optimizer to move on, because it will have the initial guess which is close to where I want it to go. So let's take PQ pose 0 for this, and then 1. So I initialize x in, I get xref from curve, I send inverse kinematics, out comes x in, the joint angles, I put them in decontrol, and this just keeps repeating. Let's see what we get from this. Okay, it looks like it pretty much did the plot. How do I verify? Well, that's going to be my last step. Okay, so once you program to draw the curve, save the data and plot in MATLAB. So I need to let's do this in MATLAB to check. Now the way I do this is there is this save data which is usable. So I'm going to save printf. This is just setting up the variables I'm interested in printing. So let's say that I want to first draw the reference xref and zref. So that's going to be the reference. Okay. Then I'm going to say fprintf with the x actual, the actual. These are the values which are obtained from sensor data. So remember here, don't put a comma, it'll give some errors when you load it in MATLAB. So then here I need to now save them. So fid percent, I forgot a comma here. %f will be, this will be the x reference. So I need to make a variable. So let me just do that later on, but let me just save that in xref and cref. And then fprintf, fid %f. %f. There should be no comma there because we get an error when you load it in MATLAB. Exact. Okay, so I need to create these variables first, and then I need to assign whatever the values are at every time step. So let's initialize it, and I want to make them global variables because these are produced at different instances, different places. So double and double the act. Okay, and now let's just save data at every time instance. First, I'll save it in init controller. Okay, so right, maybe here xref equals xref 0 zref equals xref 1, then x actual equals the sensor data. Okay, so that is only saved in the initial call. I need to do that every instant of time. So I need to go here. And then that saves sensor data. Okay, looks good. Okay, so let's run this. Printer. So we're going done. Okay, it stopped. Let me open MATLAB. Okay. So here I already have created main.m. Open that. So if you run this, it should pretty much give you a bunch of plots like figure 5, figure 4. It's basically plotting all these data points as a function of number of points. So time, for example, is a function of number of data points. Then we have xref as a function of data points. But what we want to do is we want to plot zref on the y-axis and xref on the x-axis. Same, we want to plot z actual on the y-axis and x actual on the x-axis. So let's just do that. We don't want this. Let's do plot. So first variable is time, second variable is xref. And then let's have k dotted line width. So 2 and 3, 4 and 5, and this is our actual. So let's make it red. Dash line. Hold on. So reference actual x label x y label z. Okay, this is what I got. Yes, it looks like it's off a little bit. Yes, so first of all, it doesn't complete the whole thing. So what I need to do is I need to run this for 2 pi. It basically runs, so I need to ensure that, what's that? So I need to ensure that this variable here, t, goes all the way to 2 pi. In my case, I defined omega t should be that variable. So omega t should be equal to 2 pi. In other words, t should be 2 pi divided by omega. So I need to change the time. So let's go here and change the end time. There's the end time. Okay, so let's change that to 2 into pi divided by omega. And I think this will give an error. Yeah, that's what I thought. It doesn't like that. This needs to be a constant, basically. That's why it doesn't like it being redefined. So I just call it a constant. Okay, let's run MATLAB. Okay, there it is. This is off. I think this is because of the speed. So let's just change the speed to 3.75 first. Oh no, I should run me. Okay. I think it gets a little better. 7.5. Okay, that's even better. So it looks like the speed is the problem. It just doesn't. Yeah, if I reduce the speed, probably get better. I also probably want to increase this time a little bit, so it just closes this loop. So let's say plus point, let's say 0.25. We can also move the initial position, but okay, let's just change this to 0.4 and see if that makes a difference. Yeah, that's much better. Here it is. So it's just a matter of speed. It moves. It's got a speed component to it, which the PD controller cannot quite damp out. So if you increase the damping, perhaps you'll get better results. So increase the damping, increase the gains P and D for the individual joints, and then you can maybe get it go much faster and plot the lemniscate. So I have one more slide before I'm done. And this is something which you may not have realized. I did this change in the file. There is actually a difference between how I called my controller So far, what we have seen is we have used mycontroller the way it is defined on the left side. And in this particular case, I've actually defined the code the way it is on the right side. So let me show you what the difference is. So the init controller remains the same. I just called them different names. One is my controller and one of them is my underscore controller, just to show the difference. So in previous all the previous examples we've done in this course, we've always installed a internal callback called MJCB control where we define my controller. And then we went to MJ step. So what that does is this. Let's say that we use Rungekutta method to integrate the equation. So what Rungekutta does is it calls my controller every time it wants to do advance the simulation time. So in case of Rungekutta, to go from t to t plus delta t, it has to do 4 function evaluations or 4 evaluations of my controller. So you do them 4 times. And so my controller is called 4 times. That's one approach. The approach here is on the right side is different. Here I don't have this MJCB control callback. It's not an internal callback, it's an external callback in this way. In my while condition, I called my controller and then MJ step. What this does on the right side does is basically it sets the controller first. So it computes the torque, or in this case, control command, and then uses that to propagate through MJ step. If I use Rungekutta in this case, Rungekutta is not going to be calling my controller every integration step. It's because it is not an internal callback like this, but it's an external one. So once I freeze the controls using this command, you just use those controls for all those 4 function evaluations which happen in MJ step. Now the question is, why did I use this approach, the right approach, and not the left one? The reason I did this is the following. In this case, I had to do some calculations in my controller in order to compute the position of the joints. I used in that, remember, I used this dsim, a new data variable, to do these computations. If I do an internal callback to do these computations, you will see that the code will become recursive. That is, that dsim, the my controller will call dsim, the dsim will call my controller, and it'll just loop through infinite time and getting you nowhere. To avoid that, I actually make the callback external. So when I define dsim in my controller this way, it just can be executed first, and then command is passed to MJ step. So to avoid the recursion, I had to do this. When you are writing code for a robot, you typically are in this world, on the right side, right? You basically compute the controls and then you send it to the robot, and in that time span, which could be 1 milliseconds, 2 milliseconds, 3 milliseconds, it doesn't quite recompute the controller within that time step. So when you are using this code for robot, what I did today is more realistic than what is on the left. The left side makes the function evaluations more accurate because they're internal. Here it's less accurate, but this is more realistic.